Exploring the extreme universe with the Fermi Gamma Ray Space Telescope. Hi, I'm Judy Rackison, the Deputy Project Scientist of the Fermi mission. I'm going to tell you a bit about how Fermi operates, how its instruments work, and how we explore the interesting objects that produce gamma rays across the sky. The Fermi mission launched on June 11, 2008 from Cape Canaveral Air Force Station. It flies in a low Earth orbit at approximately 565 kilometers at an inclination of 26 degrees, orbiting the Earth every 96 minutes. The Fermi mission has two instruments: the Low Energy Gamma Ray Burst Monitor, or GBM, which has 14 detectors, 12 sodium iodide scintillator detectors, and 2 bismuth germanate scintillator detectors. They observe the entire unocculted sky, looking for transients above the background levels as they observe, and are the primary transient detecting instrument for fields such as gamma ray bursts. The Large Area Telescope, which is the big box on the top of this image, provides higher energy gamma ray observations of the entire sky, and we'll get into a little bit more details on how that works. The Large Area Telescope is a pair conversion telescope. The way it works is high energy gamma rays come in and they interact with the layers of silicon detectors in the tracker, and they split into showers of electrons and positrons, and those are eventually deposited into the cesium iodide calorimeter at the bottom of the detector. Together, this provides us the ability to reconstruct the energy and direction of the incident photon. By collecting photon by photon, we can build up maps of the entire gamma ray sky. So, taking a couple of steps back, what are gamma rays? Gamma rays are the highest energy form of light, but they actually cover many, many orders of magnitude in energy or frequency, almost as much as the rest of the spectrum combined. There are different techniques to detect gamma rays at different energies, starting from even hard X-rays in the tens of kiloelectron volts up to megaelectron volts and gigaelectron volts, and even occasionally the Fermi can detect teraelectron volts. There are other techniques at even higher energies from the ground, and Fermi works with the ground-based very high energy telescopes regularly to do observations of the sky and learn about the objects that we detect. The Fermi-LAT has a large field of view. It observes about 20% of the sky, and it builds as a map of the entire sky as it orbits the Earth by spending every other orbit, one orbit pointing slightly north and the next orbit pointing slightly south. And by repeating this pattern over and over again, we can build up a deeper and deeper map of the entire sky. What this looks like is something like this, where this is a map in galactic coordinates showing you what the Fermi-LAT field of view might look like as it detects parts of the galaxy and as well as other areas of the sky. We collect photon by photon, and by doing so over various timescales from even milliseconds, where we can detect some transients, up to now more than a decade, by collecting over 1 billion photons, we build up a map of the sky in more and more detail. You might see some familiar features here. What this is the Milky Way. Although the Milky Way in the gamma rays looks quite different than the Milky Way in the optical. We have the galactic center right in the middle. We have bright sources in the galactic plane. Many of those are pulsars or supernova remnants as we detect them in high energy gamma rays. We see wispy structure, which is the diffuse interstellar emission, which largely comes from cosmic rays from interacting with the medium in the galaxy. And we also see hundreds of dots above and below the plane. In fact, actually, there are thousands of these sources detected. Those are primarily blazars, a particular type of active galaxy. You may notice some interesting features near the galactic center. Some of these are known at other wavelengths. But one of the most unique features that we detect in the Fermi data are these structures that are known as the Fermi bubbles. These are enormous structures above and below the galactic plane that are detected at high energies, mainly above a GeV, and they extend almost 50 degrees above and below the plane. There are now that they've been known for about a decade, counterparts have been detected for similar structures now in the microwave and in the X-ray bands. And what we think that caused this is some sort of activity millions of years ago at the supermassive black hole at the center of the Milky Way produced probably some sort of accretion episode, produced emitted gas and a structure that has been just slowly expanding ever since. And when we look really, really deeply, we can see this interesting activity of the history of our galaxy. As I've mentioned, we detect many types of sources with Fermi. This is another map of the whole sky, except this is showing you individual sources in some of our catalogs. We have all sorts of catalogs we produce with Fermi, given that we see the entire sky. General catalogs, gamma ray burst catalogs, active galaxy catalogs, pulsars, novae, supernova remnants, pulsar wind nebulae, and the list goes on and on. In fact, we have high energy catalogs and low energy catalogs because there's a lot of different ways that you can slice our data. So these are the sources that we detect persistently over building up a map of a number of years. Some of these do vary with time, but they're not what we would call necessarily transients, and we'll get to transients a little bit later. I'm going to highlight a few of these types of sources that we particularly study with Fermi that you might be interested in. Pulsars. We detect a lot of different kinds of pulsars with Fermi. The Black Widow pulsars are a particularly interesting variety. A pulsar is a dense neutron star, a remnant of a previous massive star that's collapsed. But pulsars are unique because they spin very, very quickly. They can have timescales from milliseconds to seconds in which they emit. Black Widow pulsars are particularly interesting because they are in a binary system where the companion star is being gradually ablated by the emission from the pulsar in the gamma rays and in the radio, and that's causing the companion star to gradually lose material, hence the name Black Widow pulsars. So that's one particular type that's interesting to Fermi. Novae are another type of binary system that are particularly interesting. These are white dwarf stars that are in an orbit with a normal type star, where they're accreting some material from their companion star. A white dwarf has a real distinct limit in which it is stable, and when it reaches masses above that, it can have an episode of eruption where it emits a shock wave of material out of the star. These are known as, these are regularly seen as bright optical transients, and in the X-ray as well, and that's been seen for decades. It was only with the Fermi mission that we discovered that these also produce high energy gamma ray emission. And the source that we believe that comes from is that the shock wave sort of interacts with the wind of this companion star, and that produces a blast wave that produces gamma ray emission in the days after the ANOVA erupts. Gamma ray bursts are another famous source of transients that Fermi detects. The Gamma Ray Burst Monitor is currently the most prolific detector of gamma ray bursts flying, and the Fermi-LAT also detects a subset of these gamma ray bursts, an interesting subset that tend to be the most energetic. This animation is showing you the positions of actual gamma ray bursts from the first few years of the mission, which are randomly distributed across the sky and randomly in time. GBM detects approximately 240 gamma ray bursts per year. And we know that these come from outside of our own galaxy, both from the distribution being evenly across the sky, and also from observations, multi-wavelength observations we get across the electromagnetic spectrum, including often of the host galaxy itself, where this event occurs. A gamma ray burst is produced by two different types of phenomenon. One is the merger of a neutron star, which I'll describe next, and the other is a massive star that collapses. Either way, they form a relativistic jet, and that interacts with its surrounding environment. One of our favorite gamma ray bursts of recent years is an event known as GRB 170817A. This gamma ray burst looked fairly normal to Fermi, but as it turns out, it had a little friend. The gravitational wave network, LIGO and Virgo detectors, detected a signal of a in-spiraling binary neutron star system 1.7 seconds before this gamma ray burst. This was a really momentous discovery in that it proved that short duration gamma ray bursts, at least a subset of them, are produced by neutron star mergers. It was also the first detection of a neutron star merger in gravitational waves, and led to one of the largest follow-up campaigns of recent decades, with more than 70 telescopes contributing across the electromagnetic spectrum and from the ground and from space. But what really happened in this event? We saw many different emission components, and this animation will demonstrate what those are. We started with a binary neutron star system that after about 1 billion years got close enough together to start inspiraling rapidly and producing gravitational waves. They merged together, and then this central object, black hole or neutron star, produced relativistic jets of material that produced the gamma ray burst itself. Neutron-rich material surrounding the event produced a rapid process nucleosynthesis, producing heavy elements, and we detected an afterglow, which is the result of that relativistic jet interacting with the surrounding environment. Another interesting phenomenon that we have in recent results from Fermi is on the topic of magnetars. Magnetars actually present themselves in a lot of different ways in high-energy observations. But this particular result was about a magnetar in a nearby galaxy. This magnetar had a giant flare. This is something we previously seen in magnetars within our own galaxies. These are very, very highly magnetized neutron stars. We've seen them in our own galaxy and in some nearby galaxies. What was particularly remarkable about this event is that it was localized by Fermi combined with the WIND telescope, Mars Odyssey, and SWIFT using the Interplanetary Network, IPN, to the Sculptor galaxy, which is a nearby galaxy that's been well studied. It's only about 3 megaparsecs away. Another amazing thing about this event is that we detected GeV photons from a magnetar giant flare for the first time. And where we think this came from was that this magnetar had some material surrounding it from previous ejection events, and this giant flare, which produced particles and photons, interacted with that material that was surrounding the event and produced a bow shock. And that's what lit up and produced the gamma rays. Another interesting source that we've learned a lot about with Fermi over the last few years are blazar flares. While we've detected these throughout the mission, there was one in particular in 2017 from the blazar TXS-0506, which was accompanied by a high-energy neutrino detected by the IceCube Observatory. A blazar is a supermassive black hole at the center of our galaxy that is actively accreting material and producing a relativistic jet of emission and particles. While Fermi observes the entire sky every 3 hours, we monitor all of the blazars that are detectable. And this one produced a flare that was spatially and temporally coincident with a neutrino detected by the IceCube Observatory. IceCube is made up of detectors, strings of light detectors buried in the ice, deep in the ice at the South Pole. And as a neutrino comes in, it interacts with that ice and lights up these various detectors. And from that, just quite kind of similar to how Fermi-LAT works, we can reconstruct the energy and direction of the incident neutrino. Fermi was doing its thing, observing the sky as IceCube detected this neutrino, and from this we were able to associate the neutrino with this particular blazar. There were many other observatories that also followed it up and provided context and clues to our understanding of the emission mechanisms of blazar. But Fermi played a very unique role in this event. Another thing that Fermi does is we study dark matter. Fermi provides one of the best ways to detect indirect evidence of dark matter. And we search for dark matter in a lot of different ways. And although we haven't detected any distinctive signatures just yet, we know of a lot of good places to look. This includes at the center of our own galaxy and other nearby galaxies like the Andromeda, where we see a hint of an excess, which may be due to a population of unresolved pulsars, but it could be due to dark matter. We also look at nearby dwarf galaxies, which we expect to be dark matter rich, but don't have a lot of gamma rays normal astrophysical sources. So those provide really constraining limits. And we also look at other methods like axion-like particles. If you'd like to learn more about Fermi, please check us out on these various websites, and there are many more animations available at SVS. Thank you very much.